Is there a tropical cyclone about to hit northern Queensland just before Christmas? Hi, I'm Jack and I'm a meteorologist, but this isn't a forecast. On this channel, we'll be actually diving into the weather, the what, how, when, and why of the weather that impacts us every single day. So if you've been keeping an eye on the weather, you might have noticed that the BOM has identified an area of possible cyclone development off the northern Queensland coast over the next couple of days. And if we look at this animation, it seems kind of threatening. It's orange, it's circular, but if we look down at the probabilities, it's showing actually a 15% likelihood, which is actually pretty low. It's basically the same as rolling a six-sided dice. So let's actually take a look at the environmental drivers for tropical cyclone development and see why the BOM is identifying this region for tropical cyclone risk, and then talk about why the likelihood of it ruining Christmas is actually pretty low. So when I first start looking at the weather, I always start with the satellite imagery because it gives us a broad overview of the weather within the region, not just in Australia, but the things that are affecting us in the Indian Ocean and the Pacific Ocean. And I like to identify some structures and just see what's going on. So if we take our pen here, we can just start to circle some things that some things that stand out to us. The first thing is that there's this big dry patch of air here. And if you've been in the southeast or in Perth or Melbourne, in Adelaide or Alice Springs, you'll notice that the weather has been really, really hot and dry over the past few days. And that is because there is a high pressure system sitting right above this area here, which is providing some anti-cyclonic flow around it and pushing most of the weather to the south, to the north, and away from those areas. The next thing I want to highlight is this big circle patch over here. This rotating bit is a low pressure system, and we can tell because it's got very distinct cyclonic movement. It's spiraling inwards and down towards New Zealand, so sorry for New Zealand, that's probably some bad weather for you. Now if we look up towards the region that we're interested here, which is this area here, we can see there doesn't really look like any movement, but there is a lot of cloud there. So if we just zoom in a little bit, zooming in, we can see a lot of isolated thunderstorms, well, not necessarily isolated, but some small grouping of thunderstorms, lots of popping off here. If you've been watching the cricket over the past few days, you'll know that the thunderstorms have really impacted the cricket. That is a genuine observation, by the way, the rain at the cricket, watching it at the time, that you can definitely use that for weather forecasting. And we can also see up here near Darwin, we have some thunderstorm activity, and to the south of Papua New Guinea, we also have some activity here. And this is the area that is favorable for cyclone development, or this is the trough, I guess, that is potentially forming a tropical cyclone later in the week. Now, how can we tell that stuff, just by looking at the satellite imagery? Well, for the trained eye, it's a little bit easier, but, these are the things that we look at when we look at the satellite imagery. If we look at it every single day, we start to notice that there's things, specific features which are moving, specific features which are developing, and as we track it day to day, they become easier to identify. Another way to identify some of these features is to look at a different type of satellite imagery, which if we go here, we have this. This is the water vapor imagery, and what it does is it's still a satellite imagery, but it's a special filter which is only looking for water vapor. It doesn't have the same 24-hour loop as the previous one that we were looking at, but it shows us some really identifiable features like this big red patch here, which is that high pressure system that we identified all the way down here. This is dry air. Just write that here, dry air. And if we look here, that this cloudy bit is also pretty distinct, pretty identifiable, and that's because this satellite is specifically looking for water vapor. So it's going to highlight the areas where there's lots of water. So big thunderstorms here, some thunderstorms here just popping off the coast there, and some ones in the Gulf of Carpentaria here. So if we kind of take a step back and look at this big broad area of lots of thunderstorm activity, is this a feature in and of itself? Are these lots of small little features part of one big feature? Well, the answer is probably yes. There's this feature called the Madden-Julian oscillation, the MJO. And in a simple term, it is a standing wave which moves around the equator about once every 30 to 60 days. The more we talk about the weather, the more you'll become familiar with this stuff, but I like to think of the atmosphere as it's not a gas, okay? Air individually is a gas, yes, but the atmosphere itself, made of air, it actually behaves more like a liquid. And liquids use waves to transfer energy. If this is all moving, so the Earth is moving under the atmosphere, the sun is moving across, which is providing heat, and all of this combined create these features. Or in liquids, the longer you have energy being pushed in, the more often you get standing waves present. And the MJO is just a standing wave that is a feature that, like I said, moves around the equator about once every 30 to 60 days. We don't necessarily understand exactly how it's formed. It's quite contentious from the way that I understand it. Well, not contentious, but it's quite complex scientifically. But it is a trackable feature. And what it does provide is a pre-existing low pressure system or pre-existing region of low pressure, which is part of cyclone development. And if we go to the Bureau's page here, we can actually track the MJO. Let's just start at the initial point. This black and grey line actually tracks the MJO, or this grey line tracks the previous position of the MJO. And then the black line is the forecasted movement of the MJO. And if you look at this graph as a top-down view of the Earth, you've got the maritime continent, which is Indonesia. You've got the Western Pacific, which is like Hawaii, Tonga. Then you've got West Africa and the Western Hemisphere. That's like the US and Africa. And then back into the Indian Ocean, and then back to the maritime continent, which is Indonesia. So it makes this circle path every 30 to 60 days. And we can track it, and they use a lot of really complicated mathematical techniques to forecast where it might be going. And that's what this black line is. Basically, it's an average of all of these squiggly lines tracking where the MJO is about to go. And that is really important for cyclone forecasting because, as I said before, the MJO provides that area of that pre-existing area of low pressure, which then can become a seed for tropical cyclone development. So if we look here, that right now the MJO is currently in the maritime continent. It was in the west, it was in the northwest. So if we go back to the satellite imagery here, just as a reference, if you remember a couple of weeks ago, we were looking at possible tropical cyclone development here on the northwest shelf. And that was because the MJO was in that area. But over the past 10 days or so, the MJO has slowly tracked across here and made its way to around here in the Coral Sea. When it's over the land part, so the Gulf of Carpentaria, Northern Territory, Northern Queensland here, it has less likelihood of tropical cyclone development, which is why we saw that those probabilities reduce over the past week or so. But now it's back in the Coral Sea. We're back into conditions of warm sea surface temperatures, which is another necessary component for cyclone development. Now it's back in the Coral Sea. We're starting to see that tropical cyclone development probability come up. And let's just go to the next tab here. So we looked at the MJO, and now we're looking at the sea surface temperatures here. So the Bureau of Meteorology tracked sea surface temperatures in the Australian region, and when we're looking at tropical cyclone development, we're looking for sea surface temperatures above 26.5 degrees. It's a really specific number, I know, I get that, but it's just a measured threshold for tropical cyclone development. And as you can see, this area pretty much north of the 20 degrees south parallel, all the way across northern Australia, the sea surface temperatures are above 30 degrees. So we're well above that 26.5 degree threshold for tropical cyclone development. So we have the MJO, we have that pre-existing low. Now we have confirmed we have the sea surface temperatures to support that. So we're looking at a favorable environment for tropical cyclone development, just in those two initial conditions. There's actually 5 conditions which are required for cyclone development, and we're going to step through those in the next couple of slides. Just taking a look at what the Bureau's forecasts are saying, because then we can start to look into the mind of the Bureau forecasters as to why they're putting that probability up there. This is the ACCESS, which is the Australian forecasting model, ACCESS S in this instance, which is just the broad scale model for climatological forecasting, so long-range forecasting. If we look at the South Pacific tropical cyclone occurrence in the next 2-week period, it is identifying a probably 5 to 10% likelihood of cyclone forming in the Coral Sea region here. It's a little bit hard to see, so I'll just circle it here, but this is the area that we're looking at. So the Bureau of Meteorology's model, ACCESS, is doing a big bunch of calculations about what the climate will look like in the next 2 weeks. And it's saying, okay, there is some areas where we think that tropical cyclones may form. And, that is a good place to start for the Bureau forecasters, because they start to look at that area and they say, okay, the model has identified this area. Now let's have a look at the specific environmental conditions to see if it is favorable for cyclone development. And then they start attaching probabilities. Just for a little bit of verification, let's just have a look at ECMWF. It's a lot of letters, I know. It's the European model for forecasting, and it's a pretty reliable forecasting model for the Australian region, which is why we like to use it or compare it to ACCESS. It's important to compare two or multiple models together because the models use different data, they use slightly different calculations and pre-existing conditions in order to create those forecasts. So you never want to rely on a single forecast. We always want to compare two, look at the features that are forming, see which ones are picking those features a little bit better in comparison to what is actually out there. So we'll just go back to the satellite imagery here and we'll say, okay, well, is ACCESS picking out these thunderstorms, or is EC, the European model, is it picking out this area of this high pressure system here, this dry area here? Which one is doing that more accurately? Okay, it's ACCESS today and it might be EC tomorrow. Okay, well, we'll look at what EC is saying. If it's EC today, we'll look at what EC is saying and we'll compare that to what ACCESS is saying. So this is EC's ensemble model. So it will run a whole bunch of different forecasts and kind of take the averages. What this specific one does specifically, the ensemble, is looks at areas of low pressure and pinpoints where those are. And what we're looking for is grouping. Definitely in the weather, when we're weather forecasting, anything that looks like a bullseye is what it is. Bullseyes are always a really good indicator that there is something happening there, either in the model or in the atmosphere if we're looking at the observations. Bullseyes are good. So we're looking at this bullseye here starting to form and the EC ensemble. So lots of different model runs within the EC model itself is running, and it's saying, okay, well, there's a lot of low pressure systems forming here in the 100 or so different model runs that we've done, and then it starts to move offshore. And actually, if we go back to the original forecast here that the Bureau puts out on their public page, we can see that actually that kind of looks similar. It's behaving in a similar way to what the EC model is saying. We're seeing this area here. We'll just go back a couple of days. We're saying that there is a identified cluster of low pressure systems in the model. They're forming offshore in the Coral Sea and then moving away into the South Pacific. Okay, so we've got a little bit of verification here, not just between the ACCESS model, the Australian model, the EC model and the ensembles in it, or the different model runs in it, and then also what the Bureau's experienced forecasters are pushing out into the public forecast. So there's a little bit of confirmation here. So now the question is, why is the probability so low? We've seen that we have a pre-existing low pressure system there, which is the MJO. We've seen that the sea surface temperatures are able to support tropical cyclone development. Okay, so then why don't we see that higher probability? Why don't we see a tropical cyclone forming? In fact, the conditions are there almost today. If we go back to here, the conditions are over the past 24 hours, we're starting to see, lots of low pressure systems forming off here. The MJO is definitely tracking here. So why aren't we seeing a tropical cyclone form today? Well, the answer is that there's a couple of other factors I alluded to before that are required for tropical cyclone development. And one of them is little to no shear. Now, what is shear? I did explain it in the last video, but I'll draw it again just so you don't have to go back. So shear it's not a meteorological term, it's just a physics term. And it's what happens when you have a structure or you have something, and it is moving where the bottom is moving in a different direction to the top. So, you can look at the bottom of the atmosphere here. This is actually the ground, the bottom, and we have the top of the atmosphere here, which is actually the tropopause. I'm just going to put tropopause, TP. And let's just say that the ground, the air at the surface is moving in this direction here, and then the air at the tropopause is moving in this direction here. So if you're a cyclone is something that has, something that's big, it has structure. If you're a cyclone that is sitting here, swirling like this, like up, like this, what actually happens when it's the top and the bottom are moving in different directions? Well, it actually just cuts it in half. So what it does is it just breaks up the structure that forms the cyclone and doesn't allow it to form. So how do we assess shear? Well, it's a little bit hard, but we take observations from the ground and we can take observations from the top of the atmosphere and then compare those two together. It's literally just a vector sum between the two. But, just for the purposes of visual identification here, it's probably just easier to look at the models. I don't normally like to look at the models when we're trying to identify environmental factors because the models can be wrong. That is why we compare particular models like we saw before. But for visual purposes here, we can say that the model is displaying that this EC model is pretty accurate. We've already assessed that compared to the observations that we were looking at. And we can say that, okay, maybe the EC model is a pretty accurate representation of what the atmosphere is doing right now. And we can look at the shear. Areas where it's blue is low shear. Oh, that is not a good color. Areas of blue, that's also not a good color, but is where there is low shear, and areas of red is where there is high shear. So as you can see, we can kind of track. Let me just start again. If I start the animation again. So if we can track this area of blue that moves across here, that is actually kind of associated with the MJO. It's almost a feature of it, which is why we see those that pre-existing low pressure and those thunderstorms form. We do have that, but it does get broken up by these areas of larger shear just to the north and this really strong area of shear to the south. So although there is an area of low shear that is kind of sitting in the area, it's not very broad. It's actually it's being squeezed between these other two areas of high shear. So we would say that area is probably not very favorable in terms of shear for tropical cyclone development. So that's one factor. Okay, what's the other factor? The other factor is something called upper level divergence. That's a little bit harder to explain, but we'll try and draw it here and hopefully it makes sense. So we've already established that the atmosphere has a bottom, which is the ground, and a top, which is the tropopause, and the cyclone sits in here. It has structure like this. So say that we have favorable shear through the column, through the atmospheric column for this cyclone to develop. Hopefully it makes sense when I say this, but a cyclone is just like a big vacuum, right? It's sucking things towards it. If you've seen a cyclone on satellite imagery, or if you've seen the movie Twister or something like that, you'll know that the cyclone creates these really strong winds and it sucks all of the winds towards it and upwards. So sucks everything in and up on both sides. Now remember when we talked before about how the atmosphere is a fluid, or we like to think of the atmosphere as a fluid. So when you've got all of this air coming in and up, where does it go once it hits the tropopause? For some physical reasons we won't get into in this video, but the air can't necessarily escape past the tropopause, even though it is actually only just air above it or slightly thinner air. We consider the tropopause as being almost a hard stop, similar to the way that the air can't just go down into the ground this way, can't just go like that. The air has to come in and go up. So where does it go? Once it comes in, up, it also has to come outwards like this. It comes up and outwards, because we can't have a grouping of air. We can't just have all of the air being sucked in and then sitting in one place. It doesn't just accumulate in this area here. The same way that if you if you're in a pool or if you're in the bath and you try to grab some water and move it to another place, what happens to the water around it? The water just comes in to fill that space that you tried to pick up and pull away. The water is always moving into empty space. So this area is coming up, in, and out. And this outwards movement is what we call divergence, upper level divergence. Does that make sense? If you have those three words together, upper level, so upper level of the atmosphere, upper level divergence. The air is moving away. And in order for a cyclone to develop, you need to have that divergence coming out. The form that divergence takes often is in the form of a jet. A cyclone will form close to or on the equatorward side of a jet, which provides that airflow outwards. It's almost like the air is being sucked out of the cyclone into the jet and then moved to another place. It's hard to see that on the satellite imagery, and we might actually be able to see that here. Actually, the water vapor is a much better way of looking at that divergence. So let's just say that this area here is a cyclone. It's a big storm, and a big storm is reaching the top of the atmosphere, and it still requires that upper level divergence in order to have that favorable environment. So this isn't a bad example to start with. So you can see here that there is air. If you kind of squint your eyes, take a step back, go back to the screen, take a look again, you can see that the air, this kind of wispy air at the top here, this is all upper atmospheric cloud, and it's all kind of moving in this direction. And if we go a little bit further down, we can see that jet, which was identified in the model animation that we saw in the previous slide, there was that jet that was sitting below, and that the border of that jet is actually here. And you can kind of see, again, that the general direction of airflow here is this way. This is divergence, okay? Or this is the atmosphere pulling the air away from this area here, or not necessarily pulling, but it's moving away. So for cyclone development, we need those 5 factors. We need the pre-existing low, which is the MJO. We need the sea surface temperatures above 26.5 degrees. We need little to no shear between the bottom and the top of the atmosphere. So that's the shear that, if there's high shear, it just cuts the cyclone in half and breaks it up. And then we need upper level divergence for that cyclone to form. So the last criteria that we need is a latitude between 5 and 23 degrees latitude north and south of the equator. Maybe ignore these lines a little bit. They're not super accurate, but this is what we're looking for. So tropical cyclones can only form in this region here. The reason for that is Coriolis force. We won't go into it here because it's quite complicated. We will talk about it in other videos, but that is the 5th and final requirement for tropical cyclone development. So first of all, when we're going back to the Bureau's forecast here, what have we got? We have a pre-existing low pressure system. We have the MJO sitting in the region. We have sea surface temperatures above 26.5 degrees. We have moderate shear, okay? That is a critical element, a moderate shear, but we do have a strong jet in the region, which is causing some upper level divergence, and it is in the right latitude. Actually, this is a good thing here, because if we see here, the tropical cyclone down to 23 degrees here, so it is in that area, which is favorable. So what I think is that although this area has some factors which are favorable for cyclone development, the thing that is going to stop it is the shear. There's just too much shear in the column to be able to let that cyclone develop a structure from the bottom of the atmosphere to the top of the atmosphere. Okay, so that doesn't necessarily mean that it's going to be good weather for northern Queensland leading up to Christmas. Those factors are still there, and they're still providing a lot of moisture and a lot of cyclone-like development over the next few days. If we go to windy, we're looking at the models. We like windy because it can give us both ECMWF and access models, so we can do some comparison. And, just going on what I was saying before, comparing the two models, if we just flick between the two models on this day, we can see that there is a bit of a difference in the structure. A lot of the features are there, but the structures are different. And that just goes to show the difference between the models, even on the initial day. So this model run time now should be the most accurate, because as models go along further into the future, they become less and less accurate just due to general chaos. So if we go to ECMWF, I think because we've decided that it's probably showing us a little bit more accurate representation of the atmosphere, we're looking at a large blob of rain, which is going to be affecting the coast kind of around the Townsville area to the north and out into the South Pacific over the next week or so, and then spinning away over Christmas. And then that trough becomes pretty distinct and curly over New Caledonia and Vanuatu Christmas Eve, and then moving further away. So we can say that although the conditions are probably less likely for cyclone development, we are still going to see a lot of rainfall north of Townsville over the next week or so. But good news is that system looks like it will continue to be moving out into the Coral Sea and away towards, unfortunately for New Caledonia and Vanuatu, rainy for them over the Christmas period. And now that we've actually looked at a lot of different sources, we've looked at the satellite imagery, we've compared different models, we've looked at the pre-existing environmental conditions for cyclone development, we can actually be pretty confident in this forecast. And that's really it for this video. Really what I want to explain is that this channel isn't about forecasting. If you want to get your daily weather forecast, you can watch the news, you can look at the Bureau of Meteorology app, or there's other channels on YouTube which are providing really good forecasting day to day. What I want to do is look at the actual weather, look at the atmosphere, look at the conditions and the what, how, when, and why of the weather that impacts us. So thanks for watching. And I'm pretty new to this channel and I'm new to making content like this. So if you like what you see, like the video, subscribe to the channel, and give me some feedback in the comments. Tell me what you want to see. Tell me about the weather things that you want to learn more about, and hopefully we can talk about them in further videos.